Okay, so welcome back. This is the final session of the workshop, and I hope that if you were looking for answers, you found some, but we still have some questions, obviously, from Bobby, Gramacy. Please, you can start.
Thank you. Yeah, I only have questions for you, no answers. Thanks very much, and thanks for staying to the bitter end here. Try to make it sweet. All right, this talk is about Gaussian process regression as a means of surrogate modeling. So apologies, this is the umpteenth one of those in this meeting. So I'm working with computer simulation data, but I'll tell you what's unique about it a little bit later in the talk. This is my quick slide on emulation. An emulator is just a regression, a response surface fit to training data, XY pairs. Gaussian processes are the canonical version of that for many reasons. One reason, I think, is because of analytic, or at least partially analytic, tractability. So a Gaussian process model is just a multivariate normal model for the responses, where most of the effort is spent in the covariance structure, which is defined as a function of distance and some unknown hyperparameters. Putting a mean structure in the multivariate normal is very important, but I'm going to dispense with that and just do mean zero, because most of what I'm working on has to do with the covariance structure. You get nice accurate predictions from this framework, good coverage properties, interpolation if you have a deterministic computer simulator that you're working with. I'm going to back up a little bit and do a bit of review. Hopefully there are still some applied mathematicians in the audience that they might get something out of this. Let's see. So here's a quick review. The main reason for reviewing is to show you how I've been thinking about estimation for challenging Gaussian process problems, which is very different from how I started thinking about it when I was a much younger statistician. So people talk about Gaussian process priors and then posteriors. So what does it mean to have a Gaussian process prior? Or what's the essence of it, at least in my opinion? Well, you can generate random functions by building a correlation structure and taking draws from a multivariate normal distribution. So if I take a very special case of what I had on the previous slide and build a covariance matrix just by e to the minus Euclidean distance, so that's what's up there on the right-hand side, and then I draw n-variate y vectors from that multivariate normal and then plot them as y versus x, then I get a nice smooth function. So here's some R code that does this. By the way, this gives me the opportunity to say that this is a new experiment for me. I've been doing talks that are with the attempt to be as reproducible as possible. So all the R code runs and it generates the stuff that you see on the plots. So here's a little setup where I just take 100 x locations evenly spaced between 0 and 10, and I calculate their pairwise distances and then do e to the minus distance, and then I draw 3 n vectors from a multivariate normal with that covariance matrix. And I can plot those 3 n vectors as curves. So these are samples from a Gaussian process prior. It's a function generating scheme. Of course, we're not usually in the business of just generating random functions. There might be some uses for that, but we don't find very many of them in practice. What we really want to do is, given some data, ask what random functions support that data. So if I just showed you samples from the prior, before any data were involved, what we really want is a sample from the posterior under the Gaussian process prior assumptions. Okay, so that's a very Bayesian interpretation, but I think the essence of the calculation is simpler than that. It's just a fact of conditioning from multivariate normal data. So here I pulled this directly from Wikipedia. If you go to that link, you see exactly these formulas. So it says if you have an n vector partitioned into 2 groups, one of size q and another of size n minus q, then you can work out the distribution of the first one, say, conditional on the second one. So if we apply that with y's as a function of x's, then we get what's on the next slide. So an instance of that helps us develop the predictive equations for y and a set of x's, which might not be in our original data set, as a function of the xy pairs that are in our data set. And we get a linear predictor, so the mean of the Gaussian distribution that describes these equations is linear in the y values, and you have a kind of quadratic structure in the variance, where variance is higher the farther your predictive location is from the training data X locations. So these are called the Kriging equations in spatial statistics. You can show that the prediction that you get from the mean is a best linear unbiased predictor, and there are all sorts of other properties that aren't super relevant for what I want to present today. So let me just give an example of that in code. I won't go through every line of the code. There's a lot of code in this talk. Mostly it's supposed to be comforting, to show you that these things aren't that difficult. They don't take very many lines of code. And so that there's no smoke and mirrors. You know that what you see is what I made with those lines of code. So I took some computer simulation data, which is really a sine function, and I evaluated it at 8 evenly spaced locations from 0 to 2 pi, and I calculated the pairwise distances, and I did e to the minus those distances, and then I did the same thing for some predictive locations. So on the bottom here, I've created a grid of 100 evenly spaced locations, more or less over the same domain, calculated pairwise distances, e to the minus those distances, and then I'm also getting the cross distances between the predictive locations and the input locations, and exponentiating those as well. And then once I have all of those covariance structures, so to speak, I can follow the formulas that come from Wikipedia. I invert that covariance matrix, I get the linear predictor for the mean, I get this quadratic covariance structure, and now I've got the mean vector and the covariance matrix of a multivariate normal, and I can take as many draws from that multivariate normal as I want, and they would summarize my posterior distribution over functions. So I've done that. I've taken 100 random draws from that distribution, and I'm going to show you those draws on the next slide, and I'm also going to calculate the quantiles of those draws so I can make error bars. So on the next slide, I have the posterior predictive distribution over this computer simulation data set, and you can see it has visually a lot of nice attractive properties. It interpolates, it's nice and smooth, it has enhanced uncertainty away from the training data locations. It has this sausage, I guess that was the first time I heard that today, the sausage. I used to call it the football shape. The sausage may be better, so I might just start using it. So that's very cartoonish. Often our covariance structures are parameterized, or some people will say hyperparameterized, because it's really a non-parametric model that gets most of its flexibility from the data locations, the end data locations. So this is a typical squared exponential anisotropic correlation structure with different length scale parameters, theta k, in the different input directions, a nugget parameter, tau squared. How do we do inference for those unknown things? Well, then, this I always find a little bit awkward. People talk about likelihoods or marginal likelihoods. The whole thing's supposed to be Bayesian and posterior, but when it comes to inferring these unknown parameters, usually what people do is they view that multivariate normal as a likelihood, and they take its log and they differentiate it and solve. Or maybe they do Metropolis Hastings if they want to be fully Bayesian about it. So here's my log likelihood that comes directly from the multivariate normal structure. And I can differentiate that, say, with respect to nu, which is my scale parameter on the whole covariance structure. And I can solve analytically for a maximum likelihood estimate. And it's like a residual sum of squares calculation. And then I can take that and plug it back in and get some kind of concentrated log likelihood and then try to take derivatives with respect to the other unknown parameters. Unfortunately, solving the likelihood equations for those parameters is not doable in closed form, but you can take derivatives pretty easily through nice rules about derivatives of matrices and get a good numerical method for maximizing if that's what you want to do. And just to convince you of that, I have coded it up. I haven't shown you the gradient of the log likelihood in math, but here it is in code. GNL is gradient of the negative log likelihood. That's all there is to it. That's all the code for the gradient. And then the function up top is just the negative log likelihood itself. And I can put this pair, objective and derivative, into my favorite optimizer, which is LBFGSB in the optim package for R, and I can get solutions pretty quickly. So let me demonstrate that to you. I'm going to create another toy problem to work with that's in 2 dimensions instead of in 1 dimension. So I've got this toy set of XY pairs. I've got a space-filling design of X's with a little bit of replication for reasons that will become apparent when I talk later in this presentation. And then my y's are given by this last line in the first group here. And I take those XY pairs and I pass them to optim with the negative log likelihood as a objective and the gradient as its derivatives, and then out pops the estimates of my parameters. I've got 2 length scale parameters. So apparently the second direction has length scales that are about 2 times longer than the first, and the nugget, which helps me work out what the variance is. And once I have those parameters, I can plug them back into my covariance structure and redevelop all of the covariance matrices using those values, and then calculate cross correlations under those parameters to predictive locations. This is all cut and paste basically from code that was in the earlier slides. The only difference is I'm using the particular values of the parameters that I've just estimated. And then I can make pretty pictures of what the surface looks like. So in 2D I still have nice visuals available to me. So this is the mean surface from the predictive equations, and this is the variance plotted pointwise for the predictive locations. And you see it has this sausage property, but in higher dimensions. The variance is highest away from where observations are collected and lower nearby where observations are collected. So I think that's all neat and tidy. That's great. So where do we go from here? I've been working with a lot of computer simulations lately that are noisy. I haven't seen many in today's workshop, but I work with folks in geostatistics and in economics and in biology and epidemiology, where they're making these huge stochastic simulators that have very low signal-to-noise ratios. And sometimes they have noises which change over the input space, and it's not easy to get rid of that with a simple log transformation or some such. And of course, in machine learning, which is a huge user of Gaussian process prediction, they have noisy data. So their data is all noisy. All right, so I'm going to address these 2 things, low signal-to-noise ratio and noise that's changing over the input space. Let's talk about the first one, which is easier, and then we'll get to the second one. One problem with noisy data is that you need more of it to separate the signal from noise. So we are kind of working in a regime where it's possible to get more data. We're still thinking about expensive simulations, but maybe not weeks, maybe more like minutes to hours. The problem with Gaussian processes is you need to decompose a big matrix to invert it, to get its determinant. That's an n-cubed operation, so that's going to limit the size of data that we can work with. What can we do? Replication helps. It helps with both things. You might know this already. I've talked to people that know this and some that are very surprised by it. So let me tell you how to work with replicate data with Gaussian processes. When everyone knows that replication can be a powerful device for separating signal from noise, it also gives you computational savings in this framework. Here's the essence of that computational savings. Just take empirical averages and empirical variances and throw away the original data. So that's what I'm doing here. I'm making some y bars, which are the average of AI replicates at a particular input x, and I'm getting some sigma I hats, which are unbiased estimates, pointwise, moment-based estimates of variance. Okay. And then you can work with those little n things, not big N. You could think big N might be tens of thousands, but if you only have it at 100 unique input locations, little n may only be 100. And then you can work with the same quantities as with ordinary kriging, but with those average data sets and with the estimated, the method of moments-based estimators, and get equations like this. Sometimes people call those the stochastic kriging equations. You can show that they're asymptotically a best linear unbiased predictor, and other things. So there's some, the asymptotic because you have to have the number of replicates be high to get stable estimates of the diagonal of that covariance structure. What that literature might not have known about is that you can do better than that. You don't need asymptopia. You don't need to even calculate pointwise averages and standard deviations because of the Woodbury formula. The Woodbury formula gets used all over spatial statistics and in computer modeling, but I haven't seen it done for precisely this. So here's 2 Wikipedia-style definitions for quickly inverting matrices by Woodbury formula with a certain structure and also taking determinants. And if we make a mapping from those D's, B's, U's, and V's to things that we have in our predictive equations, I'm just bulleting it at the bottom, I don't expect you to follow it closely, just take my word for it, you can get fast calculations. So I'm going to show you that same thing in code. I'm going to show you how we map what I call the unique n structure to the full n structure identically, so that there's no approximation, no asymptotia required. So the code here, I'm not going to go through line by line. I'm going to show you the matrices that result on the next slide. So here we go. This might be the covariance matrix based on the full set of data. I'm thinking big N is 150. So I have a 150 by 150 matrix. I represent that through the Woodbury trick as a 50 by 50 matrix and a 150 by 50 matrix. And its transpose. I also need that. So it's like these two things put together give me that one, but for the purposes of calculation, I only need to invert and decompose and invert and whatever, and determinant of that one. I don't need to do it for this one. So I can get a pretty big computational savings. And with that setup, I can make a direct equality between what I call the full n equations and the unique n equations. So the full n ones are on the left. All of the covariances are big N by big N matrices that need to be decomposed. But you can work with small n matrices and get identical mean predictive surfaces and covariant surfaces.
Can I ask a question? Are the replicates themselves independent?
Yes, we're assuming that the replicates are independent. That's right. So why is that good? Because the right-hand side of this equals only takes little n cubed time, not big n cubed time. Sure, it's still cubic, but the n obviously matters. We want that little n to be small. So I can do the same trick, not just with the predictive equations, but I can do it with the whole likelihood, which means I can use little n calculations to infer unknown parameters, which is not anything I've seen anyone do before. I've seen a lot of Woodbury trick and spatial stats, but nobody write the likelihood down in terms of only small n quantities. And you can do the same thing with the derivative, and so that all of your subroutines in your maximum likelihood calculation, which might go through the optim function with objective and derivative, all involve little n cubed calculations. So I'm just showing you the formulas. I'm going to demonstrate for you the potential of that in, again, a toy problem, but one of reasonable size. So I'm going to go back to my 2D data set that I showed you. It had a bump up and a bump down. And I'm going to create a data set that has 100 unique input locations, spaced evenly throughout the input space, random Latin hypercube design. And each one of those has a random number of replicates. Some of them may only be replicated once, but some of them as many as 50 times, on average 25 times, because it's uniform. So I have 100 times 25, I've got 2,500 locations. That's how I build the data set in the code. Again, I'm not going to take you through it line by line. I'm going to do MLE calculations, assuming I know that there's replication, and I can figure that out with a quick check, and assuming that I don't use that. This is using a library function that we built that we'll talk more about. It's starting to get complicated. I can't just put the code right on the slide. It's more than 25 lines long, or however many you could squeeze into the slide, but it's not crazy. So we've got a function called MLE home GP, so MLE for a homoskedastic Gaussian process, and I'm doing it two ways. One, not using that they're replicates, and one using that they're replicates. And you can see that the time it takes the differences are stark. Using the fact that you know that there are only 100 unique locations saves you a factor of 4,000. 400 seconds versus 0.1 seconds. It's a pretty big difference. And the estimates of the parameters are identical up to the numerical precision of the quantities that are involved. I presented this in a paper as like the first half of a paper recently, and referees say, oh, we already know how to do this. And I think many people do, but I don't think there's any software package that provides that. You'd think they would, but I guess people don't deal with largely replicated data. Maybe they don't need it. All right, so let me change gears a little bit. This is maybe more my contribution from here on out. That was a little bit of review, although some of the things were a little bit new. I'm interested in variance that's changing over the input space. Here's a toy example from that. I used this data in my PhD thesis. It's been a great data set to illustrate challenges in one dimension for Gaussian process modeling. So here's a Gaussian process model fit to this data. It's called the motorcycle accident data. It's from Bernard Silverman from the 80s. Great data set. It's in the Mass Library for Art. So you can see that this data is not very noisy in this early regime here. This actually represents very low acceleration of the helmet of a motorcycle rider before an impact. And there's an impact here at time 18 or 17 or so, and then there's a whiplash effect. And the variance is high in addition to the rate of change being high. And then it kind of dies off a little bit. I'm appealing to your visual intuition here. If you look at the Gaussian process fit, you can see that doesn't really capture all of those things. It's not able to get that the variance is low here, and it's not able to get that it's in the kind of mid-range here. It kind of focuses on the middle of the data, which is having the most influence on the likelihood. The Gaussian processes disappoint when the noise is changing in the input space. How can we deal with that? Well, this simple moments-based estimate of variance, it's a little bit unsatisfying because it doesn't allow you to maximize likelihoods and it's only an asymptotic result, but it does give you the ability to fit heteroskedasticity, changing variance over the input space. But it only does it in an in-sample way. It can tell you what the in-sample variance is. It gives no mechanism to give you out-of-sample variance because it's an independent moments-based estimate. What you really want is something that can smooth. And what the authors of that stochastic Krieging paper said is, well, you can fit a second Gaussian process to the moment-based estimates of variance. In other words, treating this like another data set, the x's and the sigma squares that you estimate, and smooth that, and then couple the two Gaussian processes together when it comes time to predict. That idea is actually earlier than the stochastic Krieging literature, which is from 2010 or so. Back in NIPS, in 1998, when NIPS wasn't really a big thing, there was a paper that coupled two Gaussian processes together in order to accommodate input-dependent noise. And it's a great idea. They introduced latent noise variables. They actually modeled the log variance. They put a Gaussian process prior under those log latent variances, and then do joint inference for all unknowns. That is, whatever hyperparameters are in the mean Gaussian process, whatever hyperparameters are in the noise Gaussian process, and what the latent variables that the noise Gaussian process is putting a prior over. And they did that all with MCMC. It's a good idea, but it's really cumbersome. When you think about the computational order of such a thing, it's basically n to the 4 times the number of samples that you want to generate from the MCMC. And I think that makes it totally impractical on all but the smallest problems. The key ingredient, though, does make sense. There's this latent noise variable. You want to constrain it so that noise changes smoothly throughout the input space. You want to give it a Gaussian process prior. So that's what I've written down here, a Gaussian process prior on a diagonal covariance matrix delta of latent variances. And you want to be able to smooth those variances through the usual Krieging equations. So that's the mean of the mean of the delta's linear predictor gives us sort of smooth delta values. There's also just special cases for this. You can cast stochastic Krieging in this framework. You can cast homoskedastic modeling in this framework. You can do the whole thing with log latent variables. It just makes the equations a little bit more complicated, so I chose to show the simpler ones, but in our package we implement both. Instead of MCMC, you can do the same thing that I just did twice. You can write down the joint log likelihood, that is for the mean of the noise Gaussian process, and you can differentiate it with respect to all the unknowns, including with respect to the latent variables, and you can shove it into your favorite solver. And it's fast. So I'm showing you the equations, not expecting you to read them, but to believe they exist. Let me show you how they work in an example. So our package has a function called MLE het GP that automatically works out if there's replication in the data and it fits this coupled set of Gaussian processes by maximum likelihood, and it's fast. It did it for the motorcycle data in less than a second. And I can, once I do the fitting, I can do the prediction. It comes with some predictor routine, which just combines two sets of predictive equations together. And I can extract quantiles from those predictive equations so I can visualize it for you. Here it is. Variance is changing throughout the input space. This is the view directly on the scatter plot of the data. This is the latent variance process, which starts low, goes up, and goes back down. The green dots are the pointwise estimates of variance that's extracted from the small amount of replicates that are available in the data. There are actually 130 odd points here, but there are only 30 or so that have any replication, and these are the variances that you get from those replicates. So you can see it varies wildly. You wouldn't want to use the green dots as a mean of making prediction. You'd want to smooth them out, which is exactly what this framework does. Here's a real problem that I don't want to go into too much detail on because I want to transition to something else. This is an 8-dimensional stochastic simulator. It's actually coded up in MATLAB, so we had to do a bunch of work to interface between R and MATLAB to run this code. But we developed a design of size 5,000 that had a degree of replication to it, and we applied our methods. Our methods are the red ones. Larger numbers are better. We're looking at a proper score that combines mean and covariance together. A lot like the Mahalanobis distance, but takes the determinant into account. So we win out of sample, we win in sample. The times are, well, hard to interpret. I probably should take them off the slide. All right, now I want to talk about design. That was what this talk was supposed to be about. So what's the best design for working with stochastic simulators like this? I think there's some surprising results in here. So I'm going to do model-based design, and I'm not going to try to do it all in advance. I really think you've got to learn what your length scales are before you go designing, because your design is going to be sensitive to those length scales. You get it wrong and you're going to screw the pooch. You're going to just have garbage no matter how much data you collect. So I'm going to do things one step at a time. I think you can do them in batch, B steps at a time if you want. I don't think anything that I'm showing you is specific to that. So we're going to start with a small n number of runs, fit a model, choose the next design point, run the computer simulator there, update the model, repeat. So that's the basic framework of the designs that I want to show you. A common criteria is integrated mean squared prediction error. Maria was talking about this yesterday. A lot of people have been looking at this again recently. It's been combed over before. Something that I didn't know that I should have known, that Maria knew, that Aaron Leatherman knows, a few other people, I'm sure Henry knows it. You can calculate the integrated mean squared prediction error for Gaussian process predictors analytically. You need to be able to maybe calculate some error functions if you've got a Gaussian covariance, or some other fancy calculations if you have them return. But it's more or less a closed form calculation. We redeveloped that integral in closed form under the Woodbury decomposition because we want to be in that framework where we're only dealing with small n matrices. Let me show you that integrated mean squared prediction error. It's going to take me a slide or two to develop the example. So what's on this slide here? This slide is showing a noise surface that I'm calling R of x, two different noise surfaces. So we have noise surface hypothesis number 1 in blue, let's say, and noise surface hypothesis number 2 in green. So x, these are the inputs. The y-axis is variance of x that I'm calling R. And I'm assuming that these dots represent observed variances at particular input locations. So I'm supposing I kind of know what the variance is at some of the inputs. So they agree at those locations. They disagree when it comes to smoothing them out. So there's two different variance hypotheses. I'm going to calculate integrated mean squared predictive error using that formula on the previous slide coded up in R in that function for those two different noises. So this imspe.r is just a function that calculates imspe for a particular variance function R. And then it evaluates that function on a predictive grid. I'll show you what that looks like. So now the x-axis is the same as before, but the y-axis is imspe. and smaller is better. You want to minimize the mean squared predictive error. The blue hypothesis is minimized here. You would take the next data point to be about 0.3. The green hypothesis would take one of the existing locations in the data, the second one here at maybe 0.35. That's where the green curve is minimized, and that's where the blue curve is minimized. It's kind of surprising that you would prefer to replicate. In ordinary deterministic computer experiments, there's no point in replicating, right? You get the same number twice. That's not useful to you. But if there's some variance, you could think intuitively that it still might not help you to replicate, unless you just thought it was a good idea. Well, the IMSPE criteria says it could be good to replicate. Indeed, the solution might be to do a run exactly where you already have a run. You can actually develop a condition under which that would happen. If your noise variance, or what you believe it to be, is uniformly bigger than something, and that thing is just a function of your predictive variance calculations, then it is going to be that every time you get a replicate. Whenever that's true, you will replicate. It doesn't say exactly where you will replicate, but you will replicate at one of the locations you have already. I've coded up the right-hand side of this inequality so I can plot it for you on the graph with the IMSPEs. So this is back to variance on the y-axis, same x-axis, and the straight dashed line is the right-hand side of that inequality. If the variance is everywhere bigger than that thing, you will replicate. And indeed, the green line is everywhere bigger than that thing. And the place where you are closest to that thing is where you will replicate. So replication is organic with integrated mean square prediction error under some conditions.
So if you would take a little bit the cost that you're saving by using these tricks when you replicate, maybe you would try to replicate even more. Right?
Thanks for, oh, there's a bug in here. Yeah, thanks for bringing that up. There's no bug here. It's just there. Yeah, thanks for bringing that up. I'm gonna do exactly that and one other thing. Okay, so let me transition to that. That's basically what we're gonna do. So let me summarize what we know so far. Replication is good for Gaussian process calculations. It means we can speed them up relative to the total size of the data. It's preferred by integrated mean squared prediction error under certain regimes. And intuitively, it helps separate signal from noise. One disadvantage, though, to this framework is that I say IMSPE is myopic, but most design heuristics are myopic. When you're thinking one step at a time, you're not looking forward across all of the design decisions you might make in the future. You're just saying, what should I take now? What's optimal for now? I'm not going to worry about what's optimal for in the future. And people have tried to look ahead a certain distance while they're making sequential design decisions, but it's a gigantic search space when you do that. It's very difficult to do that. However, we found that something we were calling a replication biased look ahead is manageable. What do I mean by that? When I'm making a decision now, I can entertain taking a replicate or taking a new unique location, and I can think about how that would affect my choices of replication in the future. Not my choices of everything, but just what are the locations I would get in the future to replicate at, and where would I replicate at them? It turns out that that is tractable. So we're thinking about looking ahead over the choice of what to do now, well, looking ahead over the choice of what we're doing in the future to decide what we're doing now, and taking into account that if we take a replicate now, we get a future opportunity to take a new point. Or if we take a new point now, we get a future opportunity to replicate among all the other data locations. So there's a little diagram to visualize that. We're trying to choose the xn plus first location, and we could either take a new design immediately, that's the red arrow, and then the remaining locations would have to all be replicates. I only did it out 4 steps, but you could go quite far. Or you can choose to take a replicate now, which will give you the opportunity to either take a new location immediately, or replicate again, and then take a new location, or wait yet again, and take a new location. All that we're trying to do is decide what to do at the root of the tree, but we're thinking about what we're going to do in the future when we go down the hierarchy. And this tree of decisions does not grow that quickly. It only grows quadratically in the horizon that you're looking forward, not exponentially. So it's feasible computationally. Let me give you an example. So here's a toy function we cooked up that's similar to the motorcycle data. We're not using the motorcycle data because it's just a fixed data set. We want the ability to evaluate wherever we want. So here's a function that kind of has similar properties to the motorcycle data. Right? So we want to learn that. That's the truth. We want to learn that without knowing the truth. Okay? So here's how we're going to do it. I'm going to start out with 10 evenly spaced points. That's my small bootstrapping of the process, if you will. So I've evaluated it at 10 locations, and I've calculated IMSPE with a horizon of 3, just to make an illustration. We'll talk about the horizon in just a moment. And then we're going to take the location that optimizes it. And you can see that in the first 10 locations, which go from 0 to 1, the 11th location is a replicate. The very first decision is to replicate this 0.44444 number. And then we update the fit to incorporate the y value that we get at that location. And the package comes with a function called update, so that's done quickly. It's actually done in little n squared time rather than little n cubed to add that new location.
So is it invertible if you have the same location?
Yeah, I mean, all of this works. It works anyway with the ordinary equations, but the numerics are actually better with the Woodbury trick because there is a smaller covariance matrix to work with. Yeah, it's fine. Okay, and then I'm going to repeat that a bunch more times. So here's a for loop over basically the same steps so that I can have 500 total samples. So I have 11 already, and I'm going to do 489 more. Okay. And then I'm going to make a prediction over a grid for the thing that I end up with. And I'll visualize that prediction for you on the next slide. So here's what it looks like. To help you see the replication, I've put vertical gray bars at the bottom. So the taller those bars are, the more replicates there are at that location. You can see that some locations, these 3 on the x-axis, take a lot of replicates. Overall, there are taller bars and more dense bars in this part of the input space, which makes sense. That's where the variance is highest. And there are fewer bars and shorter in the lower variance part of the input space. So when I look at this, I think it's organically doing the thing I expect. More sampling where there's higher variability. Maybe the surprising thing is that it chooses to replicate exactly rather than put a point right next to it. That's epsilon away. So that's for a horizon of 3. How do you choose the horizon? Which impacts the computational effort in a number of ways. The more you look into the future, the more calculation you do. But since we're looking ahead over replication, the longer we look into the future, the more we're biasing ourselves towards taking a replicate as opposed to a new unique location, which is a savings later. So we developed 2 heuristics, and both of them are kind of like stochastic optimization schemes. We're targeting something. In one case, we call it the target heuristic, which is just targeting a certain ratio of unique to full data locations. So if we know that we only want to have 20% of our budget spent at unique locations, the other 80% spent on replicates, then this target heuristic does a kind of stochastic modification of the horizon over time to achieve that target. This one, the one we're calling adapt, its goal ignores computation and just says, I want to minimize integrated mean squared prediction error. Choose the horizon adaptively so I get the best results according to that criteria. And we actually developed this heuristic from a really nice result in the original stochastic reading paper that showed how, with the data you have, how you would reallocate things to make it better from a reputation perspective. I'm just going to grab this from the literature and not justify it to you. It's not really our work. So let me show you kind of how that works. So there's a bunch of very similar plots that are even hard for me to read at this distance. I'm sure you can't read them from there. The first 1, 2, 3, 4, 5, 6 plots are just running an algorithm with a fixed horizon, starting with small horizon and going large. And if you look at the bottom, we start out with very little replication, more replication, even more, down to to here, which is the highest horizon, which has the fewest bars, but they're all very tall, so lots of replication. So the longer you look ahead into the future, the more you replicate. Adaptive tries to choose some sort of middle ground between them in an online fashion. And target, this one's trying to get a ratio of 0.2. When it ends, it has a ratio of 0.202. So it's pretty close. The very best method in terms of mean square prediction error is the adaptive one. It has the lowest RMSE. You can see that RMSE is decreasing from low horizon to higher horizon, and the adaptive one is the best of all of them. The target one is not as good, but it has a much larger ratio of replicates to unique locations. So that's a toy example. Let me show you a couple quick real examples before we finish. So here's one that's new to the talk. This involves a simulator of viral epidemic through an SIR model. So the underlying simulation is solving an integral with Monte Carlo, and it's a two-dimensional input space over the number of susceptible and infected individuals in the population. I don't want to go into the details of it. We took the solver off the shelf. The resulting surface is nonlinear, and it's also heteroskedastic. And it has some very high noise regions. I've noticed this a lot. I'm working with an Ebola simulator with some colleagues at Virginia Tech. And it's the same phenomenon. It's highly heteroskedastic. Just in some regimes, a little change to the random numbers that you get in interactions between individuals can cause the whole population to wipe out, or the whole population to be healthy. And then for other settings of the input parameter, all of them go to the die, or all of them go to the healthy. So depending on the inputs, there can be very different and unpredictable behavior. And that's exemplified in this simple two-dimensional problem. I'm just going to show you the variant surfaces in two different situations. This is for Horizon 1 sequential design, and this is for the adaptive sequential design. The colors are the variant surface that's estimated from the model, and they're very similar in the two plots. The numbers are the numbers of replicates at particular spatial locations. So you can see this adaptive one has taken 30 replicates at this location, which is at the edge of the space in a high noise region. Red is higher noise, which is different than the colors we usually do. So I realize now is a mistake.
Sorry, I cannot follow. How can we read the space in those plots? I mean, what is susceptible or, infected or?
Oh, sorry. This is infected and this is susceptible. I'm not showing you the mean surface though. I'm showing you the variance.
No, I'm just trying to check.
Yeah.
May I ask
Yeah.
previous slide, so the model you're trying to compute the expectation or the whole response?
Stochastic
response.
So the goal is to have the best predictions. So it's integrated mean square prediction error. So the criteria we're using is to minimize our prediction error. I'm not showing you the prediction I'm making because the point I wanted to make in this plot was to show you how replicates were chosen. Maybe that isn't what you want to know.
We just what do you, intuition on the problem. I mean, is it at a final time, for example, that you look at the situation of how many IS you have, or?
Yeah, so it is the number of infected individuals at the final time as a function of the initial conditions of the system, which is number of infected and susceptible at the very beginning.
Okay, but the model is stochastic.
The model is stochastic.
So usually you get a wide mode distribution.
That's a good question. I didn't work on this example. Probably you would get a bimodal distribution. In the Ebola example I'm working on, you definitely do. I'm thinking you don't, but maybe
you do.
You do?
Like you
Okay.
said, if it is very small, the number of infected, you die. If it is large, you can go somewhere else.
Yeah, that's a good point. So I've seen that twice, and we should look back and see if we're even doing the right thing from the mean perspective. So you're saying that this area right here is happening because there's two things that are far apart, probably.
When I simulated this thing, usually this is what happens. Depending on the number of initial infected in the population, you can just die or go somewhere else.
Yeah, I think you're right. So yeah, this could probably be revised. Thanks. All right. Well, what I wanted to say is lots of replicates are possible. Let's go with that cartoon. All right. Let's look at accuracy. So this is showing as a function of the total number of samples, including replicates, how the RMSE goes down. with exactly the thing that Danny was doing. We left out a Latin hypercube to make these predictions. So the story here is they all do about the same. Doesn't matter what the horizon is. Doesn't matter whether you use any of these targets. In terms of prediction accuracy, they all do about the same. This is a mean result. We repeated this 100 times. And these box plots are the distribution at the final time step. Mostly to show that those distributions are about all the same, which you can tell by the narrow range of the axis here. So in terms of predictive ability, if you're just focusing on making accurate predictions, it doesn't matter which of the schemes that we developed that you use. But for time, it does matter. I've been told never put a table in a talk, but this is a pretty easy table. It's just showing time as a function of horizon. So low horizon, 800 seconds, high horizon, less than half the amount, and same less than half the amount for the adaptive and the target. So you save on computing time, and you don't pay in terms of mean accuracy. However, if you also care about estimating the variance, it does matter which one you do. Remember that the IMSPE criteria is just looking at minimizing variance, not looking at finding the right variance. But if we have a higher horizon and more replication, we do a better job of finding the right variance. So this is proper score, which combines mean and variance together, mean and covariance together. And we see that the higher horizon methods, horizon 1, 2, 3, 4, adaptive and target, all have higher scores on average than the low horizon ones do. So we get a better estimate of predictive variance over the input space with more replication. Right, the last example is the one I already showed you, the assembled order problem, this 8-dimensional problem. This has a higher signal to noise ratio than the epidemic one does. And the result is the opposite. The methods that have the lower horizons do better because there's more signal in the data. So the low horizon ones come down much faster than the high horizon ones do. And the important result here is that the adaptive one matches the low horizon ones. It figures out that you want a low horizon. There is still replication in this data, but not as much as in the other example. And I didn't make a plot of scores because it looks identical. The ability to find the variance is about the same as the ability to predict the mean. All right, that's about all I had to tell you. So let me summarize with what I told you. When the mean and variance are changing non-linearly in the input space, it's still possible to get accurate fits by Gaussian processes, and it can be advantageous to have replication in the design. The more the variance is changing, and the higher the variance is altogether, the more replication you'll have. And intuitively, that must be true. Both signal and noise are changing, and replication is the only reliable tool for separating signal from noise. And finally, replication has the added benefit of giving you faster Gaussian process fitting and prediction calculations. So our package, which is called HeadGP, does everything I showed you and some more. It makes everything in this talk reproducible. We even have a version of it that does student T errors. So all the same stuff, either homoskedastic or heteroskedastic, but with the ability to support extra dispersion than the Gaussian would normally provide. So thanks for listening.
Question? Yes?
When you added a design point, sequentially you said you could redo the calculations of order n squared. Was that just for a replica, or was that for any point?
A replicate we could do faster than n squared. We can do that in order n. So for a new unique location, we can do it in n squared. We're not updating hyperparameters though. If we want to update hyperparameters, then we need to do n cubed calculations because we have to decompose new matrices. But that's just to update conditional on the parameters. So if you go back to the talk, you'll see I have two bits. Usually I'm just updating with no change of the hyperparameters, but every 25 iterations, I'm redoing the MLE calculations with a warm start, starting where they were before and then letting them, after a few iterations, update themselves.
No. So even if there's no actual error, you could use leave one out cross validation. If the leave one out cross validation error at that point you left out is bigger than predicted by the variance at that point, then you can kind of, you can normalize by your current variance, and if it's a lot bigger, then giving the indication of the actual variance at that point would be different. I've tried a bit of that in the past, a long time ago, but is that something, so you could do a sort of iterated, reweighted method where you reweight with the cross-validation indicated leave one out cross-validation error, and then you wouldn't really, then replication is not relevant because but the variance can change even though replication is not relevant.
Well, this is the first I'm thinking about it, so I don't know what the answer is. It sounds interesting.
I've done that with industrial experiments where you have because variation is very important in quality control, so you need to get the variance, estimate the variance so you can do quality control. And that's the cheapest thing you have is just to leave one out cross-validation.
And you're saying that that would produce no replicates in your design, or?
No replicates, you can do it because it's just, if the observation is bigger than predicted by the rest of the points, then the variance is too big at that point.
And you can, okay.
And then you can fit the variance surface according using the leave one out cross-validation error.
Mm-hmm.
Bit of a slight tangent. So when you're talking about replicants, you talk about essentially fixed locations in space where you have already in your data discrete locations. So when you get into really big data sets, you might be in a situation where you could possibly want to impose replicants on your design space. Have you looked to using this method for that?
So that's what the target heuristic is meant to do. It's meant to say, I don't want to have too many unique locations relative to the total. And so it just favors replication. It doesn't force anything. We tried methods where we wanted to make sure that we had exactly 100 unique locations. And we never came up with anything that would get that quite right. Because we wanted to allow some flexibility to take more unique locations now and make up for that in the future. Or more replicates now and in the future spend more of our budget. So none of the hard thresholding things we tried worked, but the soft ones tended to follow the target that we were after pretty well and manage the computational costs in that way.
So watch this space.
What's that? So watch
this
this space. Yeah.
So, obviously I've had quite a lot of experience. I mean, I tend to emulate means and variances, and for example, we do a lot of disease modelling, and the stuff I talk about when I talk about model discrepancies have different variances at different points. So my experience is that variances are much easier to emulate than means because they tend to be much smoother functions. They're not doing such dramatically wacky stuff. You know? So therefore, rather than doing a really clever design one learning about the both, I tend to try and learn a bit about variances first. Yeah, do like a one shot where I'm going to get an order of magnitude emulation for the variance, and then having got that, I can do a much more accurate estimation for mean, and then just design for means directly. And also, I can batch a bit further ahead. Because I think the one, your designs are still a bit myopic, aren't they? I mean, yeah. So I don't know what you have a feeling about sort of that alternative, because I just find it easier to do, and I know where I'm at.
Yeah. I don't disagree with anything you're saying. It sounds like a good way to proceed. The thing about me is it doesn't use my skills well. I'm better at this. You did make me think of something though. A detail I didn't talk about is that the default option in the software is to constrain the length scales for the variance process to be longer than the length scales of the mean, because the variance does change more slowly. You can undo that if you want, but that's the default.
But usually you wouldn't.
Yeah.
It is.
So in the back.
I was going to ask, in the Blade Runner future when replicants are banned, are you still going to be able to use your software?
Blade Runner? Yes.
Okay, yes, replicates, gotcha.
That's not
Gotcha. Fair enough.
Right, move on.
Gotcha.
Could you please show slide number 34? Yes. I think the graph on the right should be increasing in tails because variance increase when extrapolation.
Yes. Why is that not? So, that's a good question. It might be that I'm cutting off You know what, I'll have to look and see why. My guess is that, that this is being cut off a little bit, that actually we predicted out to 63 or something. Yeah, thank you for that. You're probably right.
There was another question. No? So if there's no other question, let's thank again.